So we begin with the definition. Quadratic equation is an equation that can be written in the form ax squared plus bx plus c equals 0, where a, b, and c are real numbers, and a is not 0. Now, the limitations on a, b, and c, well, it says right here they have to be real numbers. B is allowed to be 0. If b is 0, that will eliminate the x term, and it makes the equation easier to solve. In that case, we'll run into a case like this in a little bit. We'll isolate the x squared term, and we'll solve it using the square root property of equations. And it works out quite nicely, just step by step, and we're there. Typically involves radicals, but a lot of these, the solutions involve radicals. Not always, though. If c happens to be 0, that's okay. Still a quadratic equation because we have the x squared term. Also, easier to solve. In a case like this, it's maybe a little bit unexpected, but we should see one like this in a moment. We can solve it by factoring, and it's actually the factoring method you're supposed to look at first when we're factoring anything, factoring out the greatest common factor. What is the greatest common factor of ax squared and bx? They have that x in common, so we can factor out an x on the outside of the parentheses, ax plus b on the inside, and since 0 is on the other side, we'd be able to set each factor equal to 0 and solve the resulting equations. So if c equals 0, that's a good thing. If b equals 0 and c equals 0, I guess the simplest case, the only way this can be true, a times x squared would have to be 0, x squared would have to be 0, and the only way that's happening is if x itself equals what? 0. So that's the simplest case. Doubt if we'll run into that if b and c are both 0. The case where it fails to be a quadratic equation is the case where a is equal to 0. That kills the x squared term, and then we just have an x term and a constant term, and then it's linear, not quadratic. So procedures that we could use to solve quadratic equations don't necessarily apply in this situation. Because it's linear, the quadratic formula does not apply. The quadratic formula, you may remember, has a 2a down in the denominator, and if a is 0, that makes that expression undefined. So we can only apply the quadratic formula and certain other procedures for solving quadratic equations if it's actually a quadratic equation. So a is not allowed to be 0. If a is not 0, and we have this expression, we call this a quadratic equation in one variable, specifically the variable x, and we say it's in standard form. Now that might not be the form that it is handed to us in. We might have to go to work on it and actually put it in standard form in order to set it up where we can solve it either by factoring or using one of these other methods. But when we have the x squared term first, and the x term, if there is one, next, and the constant term, if there is one, next, and 0 on the other side, then it's in standard form, and we can approach it. Let's look at the zero factor property, and then solve some of these. This property actually goes by 2 or 3 different names: zero factor property, zero product property, zero product rule. Basically what it says is that if we have 2 numbers or expressions, a and b, and we multiply them together and we get 0 as the answer, a times b equals 0, the only way this can happen is if a equals 0 or b equals 0, or maybe both. 0 times 0 certainly equals 0. What can't happen is you have a non-zero number times another non-zero number, and you want to get 0 as the answer. Let's just convince ourselves for a moment this is true. Maybe it's just obvious that such a thing should be true. Well, let's stop for a moment. What are the possibilities if it's non-zero times non-zero? Well, maybe it's a positive times a positive. What is a positive times a positive? It's a positive. It's not 0. Maybe it's a negative times a negative. That's also a positive, not 0. And the other case, and we could cover these both at the same time, I guess, either a positive times a negative or a negative times a positive. What's that going to give you? Negative. A negative is not going to give you 0. The only way that product is equaling 0 is if at least one of the individual factors equals 0. So this guarantees us, actually, it gives us a way to find the solutions, but it also gives us a guarantee that there aren't additional solutions lurking out there that we can't see. Basically, it says it happens only if A equals 0 or B equals 0. So once we write it out, we can be sure that we have all the solutions to our quadratic equation. So to use the factoring method, it is very helpful if we have the expression factored and we have 0 on the other side. The A part to example 1 here, we have exactly that. We have a product of linear factors, x minus 7 times x plus 1, 0 on the right-hand side, so we can apply the zero product property directly and say this will be true if and only if x minus 7 equals 0 or x plus 1 equals 0. Now, with experience in practice, I'd certainly like for us all just to be able to stare this thing down and notice that 7 makes x minus 7 equals 0 true. And negative 1 makes x plus 1 equals 0 true. So those are the two solutions to this quadratic equation. But officially, sometimes there are a couple steps in the process. Officially, we solve each of these linear equations. We add 7 to both sides there, canceling the negative 7 and the positive 7. And we get x equals 7. We subtract 1 from both sides there, canceling the 1 and the minus 1, and we get x equals negative 1. So two solutions to the original equation, 7, negative 1. Alex is probably not going to require those set braces. I do prefer having the set braces when you solve this equation on the test, but generally, Alex, if there's a box, I think, and you put in the 7, you put a comma, you put a negative 1, and it should be good. If that's not good, it'll indicate a specific format for you. The order in which you type those in should not matter. 7 comma negative 1 will be fine. Negative 1 comma 7 is not an ordered pair. It's two separate solutions, and the order in which you write the elements of a set doesn't matter. B part, it's not in factored form, but this is a case where the constant term C is 0. There's a y squared term, there's a y term, there's no constant term though, so it makes it easier. We just factor it how? Factor out a y. Y times 4y will give us 4y squared, and y times negative 1 will give us negative y. So 4y minus 1 on the inside. Again, we have a product of factors. Now, in a case like this, it's sometimes possible, maybe easy, to overlook the y. The y contributes as much to the solution set here as the 4y minus 1 does. So when I think of them both as factors, if it would help you, it's not really good form, so I don't know if I want to put parentheses around the y. That's really not ever done. But whatever will help you to realize that the y also contributes a solution here. Y equals 0 or 4y minus 1 equals 0. Sometimes something equals 0. Set each of those somethings equal to 0. Solve the resulting equations. Couple of steps for the second one. If 4y is going to be 1, y is going to have to be a fraction. Looks like 1/4. Now, I didn't take the time to check the solutions in the A part. We will run into a couple or three, I think 3 distinct types of equations in this class, and they won't be surprises. I'll let you know when we run into them, where you solve them from start to finish. You do everything right, but you can still wind up with a solution or two in the solution set that don't work. So you have to check them. Now, in a case like this, there's nothing really that we've done where we run the risk of coming up with something that is not going to be a solution to the original unless I've actually made a mistake in the process of finding these. So if I have not made a mistake, these both will work. They're pretty easy to check. The 0 is really easy to check. 0 squared is 0. 4 times 0 is 0. 0 minus 0 equals 0. So obviously true there for the 0. The 1/4 that might take a little bit more work. 4 times 1/4 quantity squared minus 1/4, I'm wondering, does that equal 0? Well, square the 1/4, what is a fourth of a fourth? Would you believe 1/16? 1/4 times 1/4? 1/16? Subtract 1/4 from that. No worries about having to get a common denominator here, unless you call that 4/16. But in any case, you would just reduce that, right? Reduce the 4/16 to 1/4, and then it's clear that 1/4 minus 1/4 actually does equal 0. So sometimes it's, I don't know, I would advise you maybe not to check if fractions are involved, because it might be more likely that you would make a mistake in the process of trying to check a fractional answer like that than actually in finding it in the first place. So in some cases it can be a little dangerous to check the answer like this if it's really not necessary. But here I don't think there was a whole lot of risk involved. C part, here's where we have to dust off our factoring techniques from the previous algebra class that we've had somewhere. This one's kind of a nice one because the coefficient of the squared term is a very friendly number 1 there. When it's 1x squared or 1y squared or 1m squared in this case, we're just looking for 2 integers that we can do 2 things with. Multiply them together and get negative 15. Add them together and get 2. They have to have opposite signs. They have to have opposite signs because the product is negative. And the bigger one has to be positive because the sum is positive. So what are these integers? And we go with negative 3 and positive 5. They multiply together and you get negative 15. So negative 15 on the end, if I'm checking this factored form by the FOIL method, right? The L in FOIL gives me negative 15. The F in FOIL, the first terms multiply together. M times M is M squared. The O and the I need to combine to equal 2M. It's 5m for the O, it's negative 3m for the I, and 5m plus negative 3m equals 2m. So it gives us back the m squared plus 2m minus 15 that we need, and it puts it in factored form, which we need. So by inspection, we should be able to write down the solution set. Should we just write down the solution set here? What are the solutions? So these are the ones. Officially, we're supposed to say m minus 3 equals 0, or m plus 5 equals 0. That's the zero product property. And then we solve those resulting equations, and then we write down the solution set. But if we've got the expression in factored form, I'm thinking we should be able to if it's the leading coefficients on those m's are 1s, it's trivial to write down the solution set. So I think go ahead and do that. Now example 2, I was looking at this a little bit ago. Example 2 asks us to do something. Let me go to example 2 and make sure. Nope. Well, example 2 is going to ask us to do something kind of strange. But first, let's make sure we're good with a potentially more challenging factoring problem. There are a couple things that make this quadratic equation more challenging than the previous ones. First thing is it's not in factored form. It's not in standard form. We've got x squared terms, x terms, constant terms on both sides of the quadratic equation. So as we begin to solve this, we need to think about putting it in standard form, getting 0 on one side. Once we have 0 on one side, we want to think about factoring it. If we can get it factored, then we set the factors equal to 0 and solve the resulting linear equation. So first things first, to put it in standard form, we'd like to have, I think I want the x squared term, in fact, all the non-zero terms on the left. Would that make sense in this case? I like to keep the x squared term positive if I can, so if it's easier to do that by putting all the non-zero terms on the right, I'll sometimes do that. But here, it looks like it lends itself really, really well to getting 0 on the right-hand side. So add x squared, add 3x, add 3x, add 3 and add 3. This will cancel all the terms on the right-hand side and hopefully give us something factorable on the left. 2x squared plus 5x minus 7 equals 0. Now, as trinomials go, quadratic expressions, this one's, I mean, to have a non-trivial leading coefficient, this one's not all that bad to factor by the guess and check trial and error method. Because 2 doesn't have all that many factors, it's prime, and really negative 7 doesn't have all that many factors either. So there are not a lot of things to try. So I should probably just write down the 2 sets of factors and guess and check, trial and error, my way to it. I'm thinking of 2x times an x, or an x times a 2x. Got to put the 2x somewhere, so we put it somewhere. About the only way we're going to come up with the 2x squared. Now there are various options for coming up with a negative 7 based on the fact that I've already put a 2x in one spot and an x in the other. There are, what for? There's a 1 and a negative 7, or a negative 1 and a 7, or a 7 and a negative 1, or a negative 7 and a positive 1. I don't know if we need to write them all down to just kind of look and see how it's going to work out. What goes where? 7 goes first, right there. And a 1 over there. And what has a plus in front of it?
7.
Plus there.
Negative.
And a minus there. Now the 4 possibilities, you don't have to, I guess if you're checking this to make sure it works, you should be good with the 2x squared, you should be good with the negative 7. So you don't necessarily have to FOIL it to make sure we have the expression up above. Just OI it, right? Check the O and the I and make sure they give the 5x. So minus 2x plus 7x, that's 5x. So various possibilities, but we need to get that positive 5x in the middle. Now there are other ways of factoring a quadratic expression, and when I teach intermediate algebra, I put a lot of emphasis on the AC method, because in cases when it's more complicated than the one at hand, it's less mentally stressful for me personally to factor using the AC method. And quick overview of that, just as an alternative way of doing what we did very quickly right here. The AC method basically goes like this. The A equals 2, B equals 5, and C equals negative 7. It's the same A, B, and C that we'll use when we substitute into the quadratic formula in a little bit. A is the coefficient of the x squared, B is the coefficient of the x, and C is the constant term. The AC method is called the AC method because the very first thing you do is multiply A by C, 2 times negative 7, and get negative 14. Now the factoring that we just got through doing did not involve a negative 14. There was a negative 7, there was a 2, and we're trying to get a 5x. There's no negative 14 there. With the AC method, multiply the A by the C, the 2 by the negative 7 to get negative 14. Observe that B equals 5, and then set out to find 2 integers that you can multiply together and get negative 14, and add them together and get 5. What are those 2 integers? 7 and negative 2. 7 times negative 2 equals negative 14. 7 plus negative 2 equals 5. There they are. Now what do we do with those? We use the 7 and the negative 2 to break apart the 5x. We're going to turn this trinomial, 2x squared plus 5x minus 7, into a 4-term polynomial with a very special property, the property that it can be factored by grouping. Now there are 2 ways to do it. They both work. Sometimes one way looks a little nicer than the other. We could take the 5x and write it as 7x minus 2x, or we could take the 5x and write it as negative 2x plus 7x. Anybody that's ever done this before have a preference? Which do you like better? you like the AC method better, but well, I do too, personally. But of these two, we just got to make a decision here. 7x minus 2x, negative 2x plus 7x. Which one is better? I think I heard negative first, so I'll go with that one. Negative 2x plus 7x. So what we would do is, we'll find some more room first of all. What we would do is say 2x squared minus 2x plus 7x minus 7 equals 0. And then by our choice of the two particular terms to break apart the 5x, we've rigged this up into a 4-term polynomial which is now guaranteed to factor by grouping. We factor it by grouping by factoring the greatest common factor out of the first two terms. I'm thinking 2x. So 2x times x minus 1. And then factor the greatest common factor out of the last two terms. That's a 7. And what makes this work is when we factor the GCF out of the first two terms and the GCF out of the last two terms, the binomials inside the parentheses match x minus 1. If they don't match, the whole thing is off. It just doesn't work at all. But they match, so we factor an x minus 1 out of those two expressions. X minus 1 times 2x will give us the first expression. X minus 1 times 7 gives us the second expression. So factor out the x minus 1, and then we've got it factored. That takes longer. It's more steps, but the steps are smaller and easier to navigate, in my opinion. So either way you want to go with this, as long as you can get it factored, get it factored. But the AC method, I think, is a good sound method of doing this. Once it's factored, set each factor equals 0. 2x plus 7 equals 0, or x minus 1 equals 0. First one is trivial. X equals 1. The second one requires a couple of steps to figure out what x needs to be, and I'm thinking it's negative 7 halves. So negative 7 halves, positive 1. I think it might take a substantial amount of work to check the negative 7 halves in the original equation and make sure that thing works. I think it'd be pretty easy to check the 1. It might even be worthwhile because of the relative ease of checking that 1 to go ahead and do it. So if I were to go up here and check the 1, 1 squared is 1. So that's 1 plus, well, 2 times 1 is 2. So that's 1 plus 2 minus 10 on the left-hand side. 3 minus 10, that's negative 7. So you take a 1 and substitute it for x in the two spots on the left-hand side. You get negative 7 over there, negative 7. Take a 1 and substitute it into, well, wherever there's an x, on the right-hand side. And you get negative 1 minus 3 minus 3. Is that also negative 7? Kind of needs to be, and it is. So substituting 1 for x gives you the same number on both sides, so it makes the sides equal to each other. So 1 satisfies the equation. Negative 7 halves probably does too. I haven't made a mistake somewhere, but I don't want to take the time, and I don't think you want me to take the time to go through and substitute negative 7 halves for all 4 of those x's and just see what happens on both sides. Now, example 2, this is a new one this semester. I think you'll run into this problem as one of the Alex Gold topics. Make up your own quadratic equation, subject to particular solutions. I mean, it's one thing to have a quadratic equation handed to you and you try to find the solutions. It's another thing to have the solutions handed to you and you try to find the quadratic equation. So it says, make up a quadratic equation in the form ax squared plus bx plus c equals 0, whose solutions are negative 3 and 2, and whose leading coefficient is 5. Any thoughts as to how we might attack this? Yes.
Do you just 5 times x plus 3 times x minus 2?
Oh, put a 5 and x plus 3, is that what you said? And x minus 2 equals 0. Just looking at it, if we were to multiply this out, we would get an x squared term. Just FOIL the two binomials, you get an x squared, and then multiply that x squared term by 5 eventually, and we'd have a 5x squared, so that seems all right. If we substitute negative 3 for x right there, it would make that factor equal to 0. And so we would make the equation true. 5 times 0 times whatever would give us 0. If we substitute 2 for x right there, it would make that factor equal to 0. And so I think this would work. Now it wants it in the standard form, so let's go ahead and simplify. 5 times x squared minus 2x plus 3x is how many x? Minus 2x plus 3x. Just 1x, right? And then 3 times negative 2 equals negative 6. If we then distribute the 5 across the parentheses, it's 5x squared plus 5x minus 30 equals 0. Now at some point, we're going to want to look at the connection between an equation and a two-dimensional graph. If we were to take the left-hand side and just say y equals the left-hand side to try to get an idea of how changing the value of x changes the value of the expression, because we're particularly interested in what value of x makes the expression equal to 0. If we just consider all the possible values of that expression for different values of x, that might give us an idea of where to look to find the value of x that makes the thing equal to 0. So in the few moments before class, I hastily threw together this GeoGebra worksheet where we can specify the solutions to our quadratic equation. We can specify the leading coefficient, and it will give us a quadratic function. I know we haven't officially talked about functions in this class, but officially you were supposed to have at least limited exposure to functions in previous algebra classes, so the f of x notation shouldn't be that big of a mystery. If we just look at this, we can kind of see what's going on. So the one we had, if we specify short-term memory, if we specify that negative 3 needs to be negative 3 needs to be a solution. That does that for us. If we specify that positive 2 needs to be a solution, that does that for us. And I suppose up there, to clean it up, I might have cleaned that up a little bit better. But if I enclose that in parentheses, it might make it look a little cleaner. There we go. Got to see what's going on with that. X plus 3 is what we wrote there. Then we get this expression. Now, if we're looking on the graph of this parabola for the solutions, we want to find the negative 3 and the positive 2, which are solutions. Where do we look? Where do we see a point with a conspicuous negative 3 and another point with a conspicuous positive 2? The x-axis. See, we're looking for the values of x that make the thing equal to 0. Now, pick lots of different values of x, and we get lots of different values for this function, but we want the one that make it equal to 0, the ones. And if x equals negative 3, it gives the thing a value of 0 because the y-coordinate of that point is 0. And if x equals 2, it gives this a value of 0 because the y-coordinate is 0, and it displays it on the graph. Now, what effect does changing the value of a have on the solutions? A is right here. This 1, a equals 1 right now. We want it to be 5. It makes the graph a lot steeper, but it does not affect those x-intercepts. So changing that value of a runs a 5 right through the expression. We distribute a 5 across, but it doesn't affect the solutions. So putting a 5 out in front or putting a negative whatever out in front stretches the graph, maybe reflected about the x-axis, but it does not change those x-intercepts. So that's not a huge deal. We have a lot of flexibility. We can change that value of a to whatever we want it to be. I guess we don't want it to be 0, do we? Nope. We just have f of x equals 0, and it's the graph of the x-axis, and everything's a solution in that case. We don't want it to be 0, but whether it's 1 or whether it's 5 or whether it's negative 5, it's still going to have the same x-intercepts. So, not a bad one. That was less painful than I thought it might be. Looking at methods for solving these quadratic equations, if the expression can be factored and we can figure out relatively easily how to factor it, we solve by factoring. If the x term is missing, even if we can factor it, we might not want to go the trouble of factoring it because it's easier, if the x term is missing, to solve using the square root method. Square root method. When the x term is missing, we can solve it explicitly for x squared and write it in the form x squared equals k. And then the solutions are just the numbers, maybe real numbers, maybe imaginary numbers. Just the numbers that when we square them, we get k, and we call those numbers the square roots of k. That's really all we get. The positive square root of k, the negative square root of k, and we write that as the solution set. So square root property of equations, sorry about that. If x squared equals k, we can say x equals, well, what we'll eventually say is this: x equals the positive square root of k, or x equals the negative square root of k. And what we'll often do, right before we write that, is use the plus or minus symbol. Because these two solutions look so much alike, except for the sign in front of them, we shorten it sometimes and say plus or minus the square root of k. And whenever we run into that symbol, plus or minus, it means take that equation or just the expression and write it twice. Once with a plus, and then again with a minus. So x equals the positive square root of k, or x equals the negative square root of k. And let's break this down on when we get real solutions, when we get imaginary solutions. Suppose k is a positive number. Suppose we get x squared equals 9, something like that. Are there going to be real solutions to this equation?
It's -3.
Yeah, they're not easy to find. They're integers. X equals 3, x equals negative 3. They're certainly real. So if k is positive, we get two real solutions to this equation. What if we have x squared equals negative 16? Well, can you square and get negative 16? So 4i, what if you take 4i and square it? 4i squared is going to be 16i squared. What's I squared? That's 16 times negative 1, and that's negative 16. So one solution to this would be 4i, and another one would be the opposite of that, negative 4i. Take that square, and you also get negative 16. So a couple of imaginary solutions. And I guess we should consider the case x squared equals 0. How many solutions do we get to this? What can you square and get 0? Well, 0, yeah. You square 0 and you get 0. So that's the only solution to this, x equals 0. So in some cases, this case, you just get one solution. It's real and it's 0. Let's try this on, sorry about that, not trying to make you dizzy, I just punched the wrong thing here. Example 3. The first one, 4x squared minus 6 equals 19. We see 3 terms, but there's no x term. So we're happy about that, I'm happy about that. It means it's easier to solve. We solve it explicitly for x squared, and it's important to note that there's no x term because ordinarily, if there's an x squared term, we get 0 on one side and all the non-zero terms on the other. But it's a different approach here. We want to solve it and get x squared all by itself on one side. So I add 6, 4x squared equals 25. And go ahead, I'd like to have 1x squared on the left-hand side. I mean, we could think about taking square roots here, but it would be weird. And I really don't want to until I have 1x squared on the left. So divide both sides by 4. And get x squared equals 25 fourths. So x is what is the square root of 25 fourths? 5 halves. 5 halves. So x is either positive 5 halves or negative 5 halves. I'm thinking Alex might like 2.5. I don't know. Would Alex like 2.5 here? No, maybe not. No. Stick with a fraction. Stick with an exact answer. Well, 2.5 is exact, but if it doesn't like the decimal, it doesn't like the decimal. So I feel confident with like the 5 halves. So 2 solutions, 5 halves and negative 5 halves. And this is pretty easy to check, so I'll go ahead and do it. Take the 5 halves up there, put it in there for x and square it. 5 halves times 5 halves gives us back the 25 fourths. Multiply 4 by 25 fourths, and the 4's divide out, and it's 25. 25 minus 6 equals 19. So either the 5 halves or the negative 5 halves will do that. So checks really easily. Now the B part. Somehow the B part and the A part are related. Now if we were to take this B part, it wouldn't be wrong to do what I'm about to do, but I'm gonna suggest maybe don't do this. Not because it's wrong, but because there's a better way. What if we were to simplify the left-hand side and either square that x plus 5? Okay, first opportunity to square a binomial in this class. Let's see if it sets an awesome, wonderful tone for the rest of the class. Squaring that x plus 5, certainly we're going to get an x squared. And then how many x? I heard 10. Heard 10. Are you thinking 10x? It's going to be a good semester. All right. X squared plus 10x plus, well, 5 squared, 25, equals 16. This wouldn't be bad, right? I don't think I want to write anything more down to this until I erase this and go back and do it a different way. But if you subtract 16 from both sides, I mean, we've got an x here. We didn't have an x in the A part, but we've got an x. So we subtract 16 from both sides. What's 25 minus 16? It's 9. What two numbers can you multiply together, get 9, and add them together and get 10? 9 and 1. So you can factor x plus 9 times x plus 1 and get what solutions? Negative 9 and negative 1. So that would not be difficult. It would not be bad. And so maybe do this. But I'm not going to. Instead, I'm going to use the square root property of equations. What we have is a quantity squared equals a number. So we can apply the square root property of equations directly to this. X plus 5, if we can square it and get 16, it's got to be one of the two square roots of 16. It's got to be either the positive or the negative square root of 16, just like that. So x plus 5 has to be either positive 4 or negative 4. And what I would do is solve for x at this point. Subtract 5 from both sides. Subtract 5, subtract 5. And my advice, it's not an absolute must, but my advice would be to put the negative 5 to the left of the plus or minus symbol rather than to the right of the 4. If you put it to the right of the 4, it's possible to confuse it with plus or minus 9 or something like that. Or plus or minus, I'm not sure what you would confuse it with, but probably don't want to do that. Put it to the left of the plus or minus. And we know the solution to this equation, but still, you might wonder about this. Don't say them if well, I know you know because we just said them. But quick show of hands, who knows what negative 5 plus 4 is? Yes, we had that class, right? Negative 5 plus 4. And who knows what negative 5 minus 4 is? Right, yes, we know that. But sometimes on a test, I will see negative 5 plus or minus 4 as the final answer. No kidding. As though not quite sure what to do with that. But I know you know that you can simplify this. You can write x equals negative 5 plus 4, or x equals negative 5 minus 4, x equals negative 1, or x equals negative 9. That's what we got before, negative 1 and negative 9. This according to the square root property of equations. Don't know if this was a whole lot shorter than the factoring method. It was about equivalent, yes.
For the test, do we have to separate the answers for you? Or can we just do like negative 5, like the first answer?
The negative 5 plus or minus 4?
Yeah, can we do that if we want to separate?
Well, if it can be simplified, and this definitely can, this definitely can, I would rather that you simplify. Let's say it's not negative 5 plus or minus 4, but it's negative 5 plus or minus the square root of 17. In that case, although I would prefer, and Alex is going to demand, that you write it two separate ones, negative 5 plus the square root of 17, negative 5 minus the square root of 17 with a comma in between. I think I would let it slide on a test if you just say negative 5 plus or minus the square root of 17, because that can't be written individually, they can't be simplified anymore. But negative 5 plus 4, you can simplify that. So I would definitely want you to write them separately and then simplify them as much as possible. Yes. And let me write that so it looks like a negative 9. So the C part. We have options here. We could subtract 9 from both sides. What's 16 minus 9? That's 7. Oh! I should have made this problem more challenging. Because it still begs the question, why not just do it this way? All right? What two numbers can you multiply together, get 7, add together, get 8? 71. So we factor x plus 1, x plus 7. You get negative 1 and negative 7 as the solutions, and you're done. Why does Mr. Mizell insist on completing the square? Well, I insist on completing the square in this example because suppose that hadn't been a 9. Suppose it had been a, 19? Suppose it had been a 19, and we subtract 19 from both sides, we'd get x squared plus 8x minus 3. I don't think we can factor that. X squared plus 8x minus 3. So if we can factor it, maybe we want to factor it. But if we can't, this lends itself really well to what's going to be the method of completing the square, where we observe that the left-hand side is a perfect square trinomial. Is that what you were thinking? Or are you thinking x squared plus 8x plus 60? That looks like a perfect square trinomial. Was that your first thought? No? Well, ordinarily they won't be presented to us in such a clean, neat fashion as that. We have to construct our own perfect square trinomials in the method of completing the square. But it is. It's the square of what binomial? X plus 4. If you take x plus 4 and square it, you get x squared plus 8x plus 16. So, in this equation, if you take x plus 4 and square it, for the right values of x, you get 9. So what are those values of x? Well, x plus 4 could be either 3 or negative 3. Applying the square root property of equations, x plus 4 is going to be 3 or negative 3. If we subtract 4 from both sides, x would be negative 4 plus or minus 3. And I want to ask for a show of hands. I know everybody knows what negative 4 plus 3 is, and everybody knows what negative 4 minus 3 is. So we write it. Negative 4 plus 3, negative 4 minus 3, and then write down the solutions. X equals negative 1 or x equals negative 7. Two solutions. Could have found them by factoring. Did find them by factoring, actually. But this is an alternate way, and it's an approach we take because we know we're about to run into some quadratic equations where the quadratic expression involved cannot be factored. And we have to know what then. This method will continue to work even when the factoring method fails us. So we work toward the method of completing the square. There we go. What are the advantages of this method of completing the square? It always works. Always works for quadratic equations with real coefficients. If the coefficient of the x squared term is 1 and the coefficient of the x term is even, it even works better than the quadratic formula itself. Now, if those two conditions are not satisfied, we're going to lean on the quadratic formula. But if the coefficient of x squared is 1 and the coefficient of the x term is even, we might use the method of completing the square even if the quadratic formula might also be available to us. Disadvantages of the method of completing the square? Well, if the coefficient of the x squared term is not 1 or the coefficient of x is not even, we get fractions, we get ugly fractions, and we probably want to stay away from the ugly fractions because that leads to ugly radicals that have to be simplified. So it can be a total pain. In that case, we would use the quadratic formula instead. Example 4. Oh, this is actually what we would have had if there had been a 19 instead of a 9 on the right-hand side. So I'm kind of glad I didn't change it, I suppose. X squared plus 8x minus 3 equals 0. Since I can't think of two integers, I can multiply together, get negative 3, and add together and get 8. The minus 3, as far as I'm concerned, is in the way. This is standard form, but if I can't factor it and I'm not going to use the quadratic formula, the minus 3 is in the way, so I'm going to add 3 to both sides. Let's focus our attention on the x squared plus 8x. Good news is the coefficient good news is the x squared term has the coefficient of 1. If it didn't, if I had 5x squared there, I would need to divide both sides by 5. Really need a coefficient of 1 for the x squared term to get this going. But it is a 1, so x squared plus 8x, we just encountered this in the previous example, but we have to ask ourselves, what number can we add to that to make that into a perfect square trinomial? That's a challenge. So 16. So put a 16 there and a 16 there. Now I could ask how'd you get 16, but a good answer could be, well, it was on the previous page, right? Wasn't there an x squared plus 8x plus 16 on the previous page? Suppose that's not an 8x. I'll come back to this one in a moment, but just a quick little aside here. Suppose it had been x squared plus 10x. What number can you add to that to make that a perfect square trinomial? 25 works nicely. And that would be x plus 5 quantity squared. What if it's x squared? Let's put a minus. How about minus 14x? What can you add to that? So 7 comes into play. When we square the 7, it's 49. Because it's a minus 14x instead of a plus 14x, x minus 7 is necessary there, because if you're squaring that, twice the product of those two terms would be negative 14x. One more. X squared plus 20x plus blank. So you're thinking about, how do we get 100, just so everybody's clear on this? Where's that 100 come from?
B times 1/2 squared.
So you take the 20 and take half of it, and that's 10. And then square the 10 and get 100. 2 steps. Take the coefficient of the x, cut it in half, get 10, square the 10, get 100. And that gives us a perfect square trinomial, x plus 10 quantity squared. Okay, good. So this, x squared plus 8x plus 16, as we saw on the previous page, is the square of x plus 4. And we have that 19 on the right-hand side in this case. When we notice that number on the right-hand side is not a perfect square, then we know we didn't waste our time trying to factor that thing. It wasn't going to be factored. We're going to have a radical in each of the solutions. So apply the square root property of equations. X plus 4 equals plus or minus the square root of 19. Subtract 4 from both sides. X equals negative 4 plus or minus the square root of 19. And to my knowledge, I think Alex asks for exact answers rather than decimal approximations. Are there any, if you've worked through 1.4, does it ask you for any decimal approximations for these?
There's a separate section that wants decimals after you do this section. After
you do this, is it 1.4 or is it 1.5? Do you know? Do you remember?
I don't remember.
Okay.
It's
all right.
After this portion of.
Okay. So I'll go ahead and write negative 4 plus the square root of 19, negative 4 minus the square root of 19. This is no doubt what it's looking for in this particular example, but you'd want to be able, if called upon to do so, to punch these into your calculator and come up with decimal approximations rounded to the nearest 10th, 100th, 1000th, whatever, however many decimal places that it asks for. And additional practice problems. Let me know if you work through these and find any incorrectly worked problems. If I give you the wrong answer, somebody let me know so I can fix that. This is the first semester I've used those, and sometimes I need my students to proof my work, and I would appreciate if you did that. But hopefully there will be no mistakes and it will cause no confusion. It's quadratic formula time. In my intermediate algebra classes, I take about a half an hour. I start with the equation ax squared plus bx plus c equals 0. Require that a not equal to 0, and it's about 10 or 11 steps. It fills up either the entire board or maybe this screen 3 times. And we solve this by the method of completing the square. We subtract c from both sides, and we divide both sides by a, and we find an expression that we can add to both sides to construct a perfect square trinomial, and we work on it, and eventually we get the quadratic formula. If you follow through that procedure, solving that general quadratic equation with the a's, b's, and c's in it, using the method of completing the square, the punchline, the final answer is the quadratic formula. So we need the method of completing the square, not so much because we're going to use it on a regular basis to solve quadratic equations, but just it is the way that the quadratic formula is derived. I'm not going to inflict that derivation on you this morning. Hopefully you had the opportunity to see that in a previous class. It's probably, I should double check this, section 1.4, if the textbook author is doing her job, it's probably written in there step by step how to get from ax squared plus bx plus c equals 0 to the quadratic formula, and feel free to read through that. Or find your way to the the course webpage for one of my intermediate algebra classes and look around section 10.1 down at the bottom of the screen, and click on the YouTube video if it would excite you to watch me derive the quadratic formula. Feel free to look at that. Otherwise, do not trouble yourself with it. Let's look at the quadratic formula and how we would apply that to solve this quadratic equation. It's not in standard form. If we're going to use the quadratic formula to solve a quadratic equation, it needs to be in standard form. So to get there, I'm thinking, well, the x squared term on the left has a greater coefficient than the x squared term on the right. So I'm thinking let's get 0 on the right-hand side, all the non-zero terms on the left. So subtract 3x squared, add 5x, subtract 9. Subtract 3x squared, add 5x, subtract 9. When we do, we get 4x squared plus 13x minus 4 equals 0. So far, so good. Well, so far, so good, except for the fact, and it's a brand new semester and ostensibly a brand new set of notes, but I'm not liking this problem right from the beginning. And it's because it has too many 4's in it. And it's my fault, 100% my fault. I know you weren't feeling bad about it because it's my problem. But too many 4's in it because we have these 4's plus there's a 4 in the quadratic formula. So if you would permit me, I'm gonna change the problem just so there are not so many darn many 4's. What can I do? I can change the 3x squared to a 2x squared. That'll get rid of one of the 4's. And what will get rid of the other 4? I don't want any 4's other than the 4 in the quadratic formula. Maybe change the 9 to a 7. That looks good. Now, the possible downside is, since we're kind of editing this on the fly, is that we may end up with something that, so it's still a minus 5x, we may end up with something that can be solved by factoring and will not have radicals in the final answer. I'll be a little disappointed if that happens, but at least there won't be any 4's. It won't be the end of the world if that happens, but at least there won't be any more 4's than absolutely necessary. So, start from scratch. Sorry about that 2 minutes of your life you're just not going to get back. Let's subtract 2x squared from both sides. Add 5x to both sides. And subtract 7 from both sides. When we do, we get 5x squared plus 13x minus 2 equals 0. It's still going to have two real solutions, which I want. I don't think this can be solved by factoring. If I just wanted to give it a casual glance at the AC method, AC equals 5 times negative 2, which is negative 10. Can you think of a couple of integers you can multiply together and get negative 10, not many possibilities there, that add up to 13? I don't think so. So this cannot be solved by factoring, so it's actually a pretty good candidate for example 5. A equals 5, B equals 13, C equals negative 2. We can apply the quadratic formula by substituting. Now when I write out the quadratic formula, I'm going to replace the A's, B's, and C's by empty sets of parentheses because we're going to substitute the 5 for B, the 5 for A, the 13 for B, and the negative 2 for C. So it is the opposite of B, plus or minus the square root of B squared minus 4 times A times C, all over 2 times A. B's first, because that's what we come to first in the quadratic formula. Substitute a 13 for that B and a 13 for that B. A's next. Substitute a 5 for that A and a 5 for that A. Finally, the c equals -2 in the one remaining spot, and it goes there. These are the solutions to this quadratic equation. Now we need to simplify. Write them as simply as we can. Sometimes it involves simplifying a radical. Sometimes it involves reducing a fraction to lowest terms. We have to be careful in both cases, but we need to simplify. So up here somewhere, x equals -13 plus or minus the square root of, when we square 13, 13 times 13, 169 minus whatever 4 times 5 times -2 is. It's going to be plus 40, right? Now, whichever way is going to keep you from missing this, I would be happy for you to do. If you see there's a minus and there's a negative, and that's an even number of them, so that makes a plus, I would be delighted for you to keep that straight in your head and write the plus 40 there. If you see a minus and a negative, and you just think that's really negative, and you mistakenly put a minus instead, then I would advise you to say minus -40, and then when you write minus -40, hopefully at the next step you realize, wait, subtracting a negative is equivalent to adding a positive. And maybe write the plus 40 in the next step, or just go ahead and add the 40 to the 169 to the next step. However you want to do that is good, but it's plus 40 ultimately when we simplify this one. X equals -13 plus or minus. What I've probably lost here, is it 209 underneath the radical sign? What I've probably lost here is the ability to showcase simplifying this radical. Now, we simplify lots of radicals in intermediate algebra, and we just kind of expect college algebra students to walk in on the first day, second day of class, and know how to simplify radicals. It'd be great if I could showcase one here. I don't think square root of 209 can be simplified. It's not divisible by 4 or 9, certainly nothing even. It's not divisible by, is it divisible by 49 by chance? 209 divided by 49? I doubt it. No. Is it divisible by 81? No. I'm thinking it's probably even prime. It doesn't have to be prime to be irreducible, but I believe what we have are -13 plus the square root of 209 all over 10, and -13 minus the square root of 209 all over 10. Two solutions here. Are these real numbers or imaginary numbers? They are real. Don't see any eyes anywhere. They're real numbers. We can go to the real number line, punch these up on a calculator, and pinpoint a location for each one of these on the real number line. Two real solutions to this equation. Oh, goodness. 9:15 is when we end up this class, right? What does example 6 look like? Let's give it a shot. A equals 4, B equals -12, C equals 9. X equals the opposite of B plus or minus the square root of B squared minus 4AC all over 2A. Substitute -12 for each B, substitute 4 for each A, and 9 for the C. This one ends up a little different from the previous. 12 plus or minus the square root of 144 minus what? 144 all over 8. 2 times 4 is 8. And we know 144 minus 144 is 0. So x equals 12 plus or minus the square root of 0 all over 8. What's the square root of 0? It is 0. X equals 12 plus or minus 0 all over 8. Plus or minus means write it twice. Once with a plus, once with a minus. So x equals 12 plus 0 over 8, or x equals 12 minus 0 over 8. 12 plus 0, 12 minus 0, both equal to 12. So x equals 12 eighths, or x equals 12 eighths, or x equals 3 halves. Is that a real number?
Yes.
It is. 3 halves is real. Halfway between 1 and 2 on the number line. We will see that there's this specific situation in which we get one real solution. Previous example, we had 2 real solutions. The next one we'll see beginning of class next time, a couple of imaginary solutions, and then we'll look at the discriminant that will enable us to predict that sort of thing. At the end of class last time, we solved, we took our time, I guess, with example 5. Example 5, when we solved that, and let me just, let's see if I actually posted that, because I need to refer back to it. When we solved example 5, open up so I can rotate it. What was the number that we got underneath the radical sign for example 5? 200 something? 209. 209. The only observation I want to make about that number is that it was positive. Since it's positive, if we were to take the square root of that number, it's not gonna let me look at that. That's fine. You've got it. Since it's positive, when we look at that, we had a number plus the square root of that number all over something else, and then a number minus the square root of that number all over something else. Since 209 is positive, its square root is real. And when you input the plus, you get one real solution. With the minus, you get another real solution. So, okay, so finally it decides to show up. So you get 2 real solutions, and I'm tempted to go ahead, there they are, in sideways fashion. I'm tempted to punch those up on a calculator and actually come up with decimal approximations for them. I probably should, because in 1.5, Alex actually does ask you to solve a quadratic equation, something like this, and go ahead and input that to the calculator. So I'll go ahead and do that. A couple of ways to do this. One way to do this, if you want to use a single sequence of keystrokes, just enclose the numerator in parentheses, and then after you do that, divide by the 10. So open parenthesis, negative 13 plus the square root on the x squared button. You've got a radical up above that. So you press second and then the x squared button, and it displays the square root of 209. You want to get out from underneath the radical sign. Now if you're using the TI-83 plus, then the keystrokes are a little bit different, and it looks a little bit different on the screen because it just encloses the 209 in parentheses. In that case, you would want to close the parentheses for what's up underneath the radical sign, and then close the parentheses again for the numerator. So let me press divided by 10 and then indicate what that would look like on the TI-83 plus. It would look like actually, let's just put it down here. It would look like, open parenthesis, negative 13 plus the square root of 209, close the parentheses for the square root, close the parentheses for the numerator, and then divided by 10. One additional feature I should probably showcase if you happen to if you happen to have the TI-84 plus with the newest operating system, I'll go ahead and complete this one. Press enter. So to a couple decimal places, 0.15. You could type the whole thing again, replacing the plus with the minus, or you could press the second button followed by the enter button. I'll call that second entry. You see the word in blue or yellow right up above the enter button that says entry. Second entry will bring back the last thing you typed into the calculator. If you do that multiple times, second entry, second entry, second entry, it'll bring back the last several things that you typed into the calculator. So that can be helpful to save some keystrokes along the way. Replace the plus with the minus in that case. Press enter, and negative 2.75. So 0.15, negative 2.75, 0.15, negative 2.75. If we're rounding, not exact answers, but they might be as close as we need for whatever purpose we have for it. And the point here is that these are real numbers, and if we had to, we could go to the real number line, 0 on there somewhere, and a 1, and a negative 2, and a negative 3. Oops, left off negative 1. Negative 1, negative 2, negative 3. 0.15 would be about right there, and negative 2.75 would be about right there. And point to them and say, there they are. They're on the real number line, so the real numbers, and there are two of them. So if the number underneath the radical sign right there is positive, there are going to be two real solutions to the quadratic equation. Next quadratic equation we did real fast at the end of class last time. Let's see, looked something like, what was it? Something like this. The number underneath the radical sign was 0. And it was kind of had a unique look to it at this point. Worked our way down. The square root of 0 is 0. The 12 plus 0 and the 12 minus 0 were both equal to 12. And so we just got to one solution. 12 divided by 8 was 3/2. And certainly it too is real. It's on the real number line, halfway in between 1 and 2 on the real number line. So we talk about the discriminant in just a little bit. What we'll see is when the number underneath the radical sign is 0, the quadratic formula, there'll be just one real solution. Now the example we start with today, example 7, I believe the number, I hope the number underneath the radical sign is negative, and we'll see what the outcome there is of that. So if I will, I guess it's already there, right there. Solve 3x squared equals 2x minus 8 using the quadratic formula. I'm going to put it in standard form first, and that's pretty close to standard form. Just subtract 2x from both sides and add 8 to both sides to cancel the 2x and the minus 2x, the negative 8 and the positive 8, so that we have 3x squared minus 2x plus 8 equals 0. Now we want to use the quadratic formula here because it says so. We might want to ask ourselves, well, could we factor it or solve by factoring if we wanted to? Quick glance reveals otherwise. 3 times 8 is 24 if I'm using the AC method. I can just ask myself, can I think of a couple of integers I can multiply together, get 24, and add together and get negative 2. I suppose if it were negative 24, we could make this happen. If that were minus 8 on the end and we wanted a product of negative 24 and a sum of negative 2, that would be pretty straightforward. But the fact that we need a positive product and such a small negative sum, we're not going to be able to do this. So we use the quadratic formula. A equals 3, B equals negative 2, and C equals 8. I'll write down the quadratic formula, substituting empty sets of parentheses for the A's, B's, and C's. And x equals the opposite of b, plus or minus the square root of b squared minus 4ac all over 2a. Start with the b's. In the two places where there are b's in the quadratic formula, we substitute negative 2. For each a, we substitute 3. And for the C, we substitute the 8. And we have the solutions just like that. There they are. We just need to simplify them as much as possible and express them appropriately given the fact we're going to get imaginary numbers here. It might not be obvious yet. And yeah, I'm pretty sure that's the way it's going to end up. We're going to get imaginary solutions. And so we want to write them in the appropriate form, a plus bi or a minus bi, if that seems more convenient. In fact, if we have a quadratic equation with real coefficients, and all the quadratic equations that I'm going to confront you with are going to have real coefficients, so no worries there. If it has an imaginary solution, it will have another imaginary solution that has this particular relationship. Do you remember this from somewhere? From intermediate algebra, algebra 2, someplace? A plus BI and A minus BI, there's a special relationship these imaginary numbers have to each other. It starts with the letter C. Actually, it's two words, and they both start with the letter C. You might remember it. If not, it's okay. It won't hurt my feelings. These two numbers are complex. Certainly they're complex numbers, but I guess that one doesn't help. It's the other C word that I need. These two numbers are complex conjugates. They're complex conjugates. That's the relationship. If they have the same real part A and their imaginary parts B and negative B are opposites of each other, we say they're complex conjugates. That's the relationship the two imaginary solutions of this quadratic equation will have. Okay, so enough without saying spoiler alert. The opposite of negative 2 is positive 2, plus or minus the square root of, well, square the negative 2, get 4. And subtract 4 times 3 times 8 is going to be positive. So 12 times 8 is 96. And all that over 6. So x equals 2 plus or minus the square root of, there it is, negative 92. So as soon as we see this is the square root of negative 92, we know we're dealing with imaginary solutions, no real solutions at all for this quadratic equation. Couple things we're going to need to do. We deal with a negative sign. How do we deal with the square root of something negative? It involves I. That can be written as I times the square root of positive 92. But then we notice that the 92 itself is divisible by a non-trivial perfect square. 92 is divisible by what perfect square? It is divisible by 4. So we can simplify the radical. X equals 2 plus or minus. Now, I'm about to do that, but just a quick word of caution. The 2 and the 6. This is tempting here, because we got a 2 up in the numerator and a 6 down in the denominator, and they're both divisible by 2. So there's a temptation here to want to scratch the 2, put a 1, scratch the 3, scratch the 6, put a 3. And although ultimately we'll be able to do that, while we're doing that, we also have to scratch the I times the square root of 92 and replace it with whatever I times the square root of 92 divided by 2 is. We have to divide every term in the numerator by 2 if we're going to divide that 6 by 2. And it's not quite divisible by 2 yet. At least we don't see a factor of 2 there. So before we scratch the 2 to scratch the 6, let's see if we can simplify that radical. 2 plus or minus I times the square root of 4 times the square root of 23. All over 6. And then up here somewhere. X equals 2 plus or minus, how about 2I times the square root of 23, all over 6. Now at this point, if you know what you're doing, and you know if you can divide every term in the numerator by a particular factor and divide every term in the denominator by that same factor, then it results in an equivalent fraction. Then you're fine. Otherwise, I've got a couple suggestions. Let me make both of them and let you decide which one you like better. Suggestion number 1, factor out the 2. We've got a common factor of 2, and there's also a factor of 2 in the denominator. So factor out the 2 in the numerator and write it as 2 times the quantity, 1 plus or minus I times the square root of 23, all over, while we're at it, let's take the 6 and write it as 2 times 3. That's option 1, maybe a little bit unconventional, but it does stress the fact that 2 is a factor of the numerator and 2 is a factor of the denominator, and we can reduce a fraction by dividing the numerator and the denominator by a common factor. So, before I give you option 2, how do you feel about this? A little leery of it. Okay, let's try option 2. Option 2. We're ultimately going to want to write both these solutions, the one with the plus and the one with the minus, in the form a plus bi, a minus bi. So let's go ahead and write this single fraction as two separate fractions. Let's write it as 2 over 6 plus or minus 2i times the square root of 23, just barely on the screen there. Did it make that screen? Oh yeah, same way. Let's see, that one, over 6. Then you don't have the worry of having a multi-term expression in the numerator and just the monomial in the denominator. Basically, you've got a fresh copy of that 6 to go up underneath the other denominator. So if you want to reduce the two fractions individually, divide the 2 by 2, get 1, divide the 6 by 2, get 3, and write 1/3, you can get by with that because you still have that 6 in the denominator of the other one. And you can write that as I times the square root of 23 over 3 as you reduce that one. Now, ultimately, you want that anyway. So maybe this is the better option here. So if I follow through with that, and I want to write the two solutions, and I think I might have room for the two solutions. If I'm looking at the a plus bi, Alex may have a little bit of flexibility with it, but after you enter it once or twice and it doesn't like what you put in there, I guess you can kind of get an idea of what it's looking for. 1/3, that's the real part, plus, now the imaginary part is basically the coefficient of the I. It's the number times the I, the number that's multiplied by the I there. So the imaginary part is the square root of 23 over 3, and then you tack on the I there. And the way I've written it, it's not a factor of the numerator, it's simply, well, out next to the fraction. It's the fraction square root of 23 over 3 times I. Now, on the test, if you would like to put the I right up next to the square root of 23, that's fine. If you'd like to put the I in front of the square root of 23, that's fine. If you'd like to put the I in front of that whole fraction, square root of 23 over 3, that's fine. But you want to try to get to know how Alex is going to want this, and I think it's going to like this best. It might accept some other possibilities, but I think it's going to like this best because this, strictly speaking, is a plus b times I. And then a minus b times I. These two numbers are complex conjugates of each other. And that always happens for a quadratic equation with at least one imaginary solution. It'll have two of them. Well, if it has real coefficients. Those are the only ones we're worried about. It'll have two imaginary solutions, and they will be complex conjugates of each other. The whole plus or minus thing kind of makes that happen. Discriminant. Let's see, let's get rid of that. I think, hopefully I deleted the right one. If I didn't, it should have prompted me. Here we go. For whatever reason, I mentioned the discriminant at this point in the notes. I do not mention what it is. You're looking, you're thinking, okay, he mentioned the discriminant. Didn't even bother to put it in boldface type, and didn't even bother to say what it is. So let me try to do both those things. The discriminant, if you compare with the quadratic formula, x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. The discriminant is the expression underneath the radical sign in the quadratic formula. The discriminant d equals b squared minus 4ac. That number is going to be either a positive number or a 0 or a negative number, and the sign of that number tells whether the quadratic equation has two real solutions, just one real solution, or no real solutions at all, in which case it will have two imaginary solutions that are complex conjugates of each other. So in example 5, the discriminant was 209, I think. That's what y'all said it was. We looked at it. It was 209, wasn't it? And we found the two real solutions. We put dots on the real number line to indicate where they were. When the discriminant's 0, the plus 0 and the minus 0 gives us the same real solution. So one real solution in that case. And in example 7, when the discriminant was negative 92, we ended up with two real solutions. Each one had an I in it. Sorry. Two imaginary solutions. No real solutions at all, because each one had an I in it. So two imaginary solutions. All example 8 wants us to do is calculate the discriminant and try to answer the question, does it have two real solutions, one real solution, or no real solutions, but rather two imaginary solutions? So let's look at example 8 and see if we can crunch the numbers and come up with that. Basically, example 8 example 8, we do less work than the quadratic formula, and we get less information than what the quadratic formula would tell us. We don't have to do the whole quadratic formula. We just, the expression underneath the radical sign. We don't get the solutions, the exact solutions. We just get how many and what kind. So find the discriminant. B squared minus 4ac. That's going to be negative 182 quantity squared minus 4 times 49 times 169. Maybe a little bit of care when using the radical. Maybe not so much the, no, not the radical here, but the parentheses. The parentheses. Open the parentheses and enclose the negative 182 in parentheses, and then square. Without the parentheses, if you type negative 182 squared, it'll square positive 182 and then multiply by negative 1, which is not what we want here. Minus 4 times 49. Whoa, so sorry about that. That's one thing I really kind of prefer about the older operating system. I don't constantly have to be looking at the screen to make sure I'm not typing a lot of nonsense up in the exponent. But jump off the exponent, then minus 4 times 49 times 169 to get 0. Evidently, when you square negative 182, you get the same thing as when you multiply 4 by 49 by 169. So the discriminant is, in fact, 0. All right. So what does this tell us? Two real solutions, one real solution, or two imaginary solutions? One real solution. Just like that. B part, b squared minus 4ac equals 150 squared minus 4 times 7 times 100. Squaring 150. 15 squared is 225, so if we tack on a couple of zeros, I believe we get 22,500. 4 times 7 is 28. 28 times 100 is 2,800. 2,800. And this has got to be positive. Let's see what positive number it is. A couple of zeros on the end. 15 minus 8 is 7. Borrowed 1 from the 2. 11 minus 2 is 9. Borrowed 1 from the other 2. Is it 19,700? This is positive. Excuse me. When the discriminant is positive, there are, well, I'm not sure what I was going for there, two real solutions. And the C part, 21x squared plus 13x plus 75 equals 0. B squared minus 4ac equals 13 squared minus 4 times 21 times 75. 169 minus, I don't know what that other one is, 4 times 21 times 75 minus 6,300. It's going to be negative because the bigger of these is negative. Negative what? 6? 1, 3, 1. 6131, negative 6,131. Is that what it is? It's negative. And when the number underneath the radical sign of the quadratic formula is negative, you get two imaginary solutions. All right. In an effort, we'll look at actually this box problem in a little bit, but let me open a new GeoGebra window here. In an effort to answer the question, what's the point of the discriminant? It doesn't tell us what the solutions are. I mean, who cares how many there are if we don't actually know what they are? Well, I'll try to give an answer to that. Let's see if I can find the archer and the discriminant. I think it starts with T. There it is. The archer and the discriminant. So an application of quadratic, look at several applications of quadratic equations in the next section, 1.5. But here's one, projectile motion. For low velocity projectiles, there's a mathematical model that's reasonably accurate if we can get by with neglecting the impact of friction on the projectile. If it's something with not a lot of drag, maybe an arrow, and the velocity is reasonably low where we can neglect the air resistance, we can come up with a pretty decent model of this. If it happens in a vacuum, kind of tough, I would guess, to find a 300 or 400 foot tall vacuum in which to do this experiment. But if it happens there, then we can neglect the air resistance completely. But if it's an arrow, it's not going to have a whole lot of drag. We can probably come close. So we can express, using some basic principles of first semester physics, we can express the height of an arrow that's fired in terms of its initial height. We're going to say someone is standing at a height 150 feet above the ground, and they're going to shoot the arrow, and it's going to go, well, according to this, it kind of looks like it takes this sort of path, and I suppose it could, so long as the initial vertical component of its velocity is 83 feet per second. So we look at the vertical component of its velocity at the moment it's fired, and if it's heading upward at a speed of 83 feet per second, then we can use the 83t right there. The initial height is 150. The negative 16 represents half the acceleration due to gravity. But we got this function, unless you take first semester physics, we don't worry about where it came from. But we got the function, f of t equals negative 16t squared plus 83t plus 150, and it will give us a good approximation for the height of the arrow t seconds after it is shot. So initially, t equals 0. At the moment the arrow is released, substitute 0 for t, and you get negative 16 times 0 squared plus 83 times 0 plus 150, and that's 150. So initially the height is 150. If you substitute t equals 1, you get a number that's a little bit more than that. If you substitute 2, you get a number that's a little bit more than that. If you substitute probably 6, 7, 8, 9, the arrow is on its way down after that many seconds, and it's going to approach 0 in that case. Well, the question is this: will the arrow reach a height of 264 feet? Don't know what's up there at 264 feet above the ground, but we're wondering, will the arrow get there? Will it fall short? What's going to be the deal? So we do this. We take the height function and we set it equal to 264. And we ask ourselves, is there a real value of t, maybe a couple of them, that makes this true? Okay. If there are a couple of real values of t, maybe one time where it reaches that height on the way up, and then another time when it reaches that height on the way down, then the answer is yes. It will go that high, maybe even higher. If the answer is no, there's not a real value of t for which it happens, then the answer is no, it will not reach a height of 264 feet. So we subtract 264 from both sides. 150 minus 264 evidently is negative 114. And we take our quadratic equation and we find the discriminant. The B is 83, the A is negative 16, the C is negative 114. So we crunch those numbers, or this GeoGebra worksheet crunches those numbers, and it gets, whoa, negative 407 for the discriminant. What does this mean? It does not reach a height of 264 feet. There's no real number for which this is satisfied, so it does not reach the height. So let's see what happens. So we get a countdown. I guess we don't get a countdown. But what we do get is, okay, there's our countdown. Simple fact that the maximum height is 257.6 feet, and it does not reach a height of 264 feet. Let's try another one, and watch this number right here. Let's see if we can get a positive discriminant. There we go. Oh, it spoiled it for us. 1,265 is the value of the discriminant. Here the question's a little bit different. The initial height of the arrow, let's let it finish its flight here and start right there. The initial height of the arrow is 141 feet, but look at the initial upward velocity, not just 83 feet per second, but 103 feet per second, so it's going faster when it leaves the bow there. And we're asking, will it reach a height of 287 feet? And evidently, when we set up the quadratic equation, we get a positive discriminant. So the answer is yes. It happens at a couple of times. It happens a little after 2 seconds into the flight. And then again, 4 point something seconds into the flight. 2 solutions to that quadratic equation. Let's let the thing fly. Let's see, I guess we get another countdown. And then it goes. And there it is. It does reach a maximum height, actually, of 306.8 feet. Probably going to be some friction that's going to slow it down more than this model would tend to imply. But it's math class, not physics or engineering class. So we can neglect things like friction and that sort of thing. And idealize this. And yeah, it actually does reach a height of 287 feet twice. Once on the way up, again on the way down. And we'll look at that one in a little bit.